How space exploration has evolved over the years. On October 4, 1957, the Soviet Union made history when it lobbed a beach ball with 4 antennas stuck on it into low Earth orbit. As far as scientific payloads are concerned, the 23-inch diameter sphere didn't do much beyond transmitting a beeping sound that could be picked up by amateur radio enthusiasts. But Sputnik 1's impact on the space race, American technological leadership, and the long-term trajectory of our own space exploration program can't be overstated. In the 60 years since Sputnik 1 orbited our pale blue dot, we've pushed the envelope of what's technologically possible in ways that the Soviets could scarcely have conceived of in 1957. In this article, we'll focus on unmanned exploration, for several key reasons. While the American and Soviet/Russian manned spaceflight programs have obviously advanced and accomplished great things, humanity's manned exploration of the stars, or even the solar system, has remained largely stuck in idle since the Apollo 11 moon landing. The space shuttle was an ambitious technological leap over Apollo in some respects, but it never achieved its original launch frequency goal, and the Soviets killed their shuttle competitor, Buran. Projects like Mir, Soviet, Russian, and the International Space Station have served as research platforms and testbeds for equipment, but neither headed out into the cosmos to explore the universe. In contrast, the tremendous technological leap from Sputnik to, say, New Horizons has been enormous. The scientists of 1957 were no less ambitious in their mission goals than NASA or the ESA are today, but they had a fraction the resources and knowledge we now possess. A number of missions were killed by launchpad explosions or unexplained failures shortly after takeoff, and the probes that did successfully reach their targets often failed shortly afterwards. After several failed Mars shots, the Soviet Union refocused on Venus. Venera 1, 1961, failed mid-transit, and Venera 3, 1965, lost communications before arrival, but Venera 5, 1969, used a strengthened design and returned data on the Venusian atmosphere for 53 minutes. Venera 7, 1970, became the first spacecraft to successfully land on a planet and return information to Earth. Early probes often carried small payloads that allowed for crude, simplistic observations by our standards today, but scientists still prioritized beaming data back to Earth. Mariner 4, launched by the U.S. towards Mars in 1964, carried a camera to relay images of the Martian surface. Power was typically provided by solar cells backed up by rechargeable zinc acid batteries. The wiki page for Mariner 4 is quite instructive and lists both the scientific payloads and the challenges NASA faced in trying to get the craft to Mars in the first place. By 1970, both the Soviets and Americans had numerous failures, and a few tentpole successes, to crow about. The Soviet Mars 2 and Mars 3 missions would have deployed the first Martian rovers as early as 1971, but neither lander survived its journey to the surface intact. Meanwhile, NASA deployed its first probe that would eventually leave the solar system after our first visit to Jupiter, Pioneer 10. Pioneer 10 was the first major space mission to use a radioisotope thermoelectric generator, RTG, a power source we still deploy to this day when solar cells and rechargeable batteries are not enough to provide a spacecraft's power needs. The Pioneer 10 and Pioneer 11 missions visited Jupiter and Saturn, returning valuable information about both planets and setting the stage for what scientists called the planetary grand tour that would be carried out by Voyager 1 and 2. These probes, and the Jovian mission carried about by Galileo, expanded our understandings of the solar system and the moons of the gas and ice giants by fielding more advanced instruments, better cameras, and taking advantage of knowledge returned by their predecessors to precisely target areas of peak interest. Fast forward to today. Vehicles like Curiosity have pioneered entirely new methods of aerobraking, to allow vehicles much too heavy to be stopped by the tenuous atmosphere on Mars to successfully land. The phrase rocket-powered sky crane is still one of my most favorite descriptions of any piece of technology, ever. From Messenger's mission to Mercury to Cassini's Saturn survey and New Horizons' exploration of Pluto, we've seen multiple generations of spacecraft push the limit on what's possible, while conveying information about our most distant neighbors in the solar system with a depth and detail that was unfathomable 60 years ago. Space is an unforgiving environment that doesn't allow scientists to rely on the same technology that we use here on Earth. You can't use a standard microprocessor for interplanetary explorations without cooking it in radiation. But as years have passed, we've still improved the performance of the computers we put in orbit around distant planets and celestial objects. Meanwhile, advances in everything from computer modeling to chaos theory have helped us tease more information from marginal signals or find new ways to rescue broken equipment. The failure of a second reaction wheel could have sunk Kepler's mission once and for all, for example, until scientists discovered they could use photon pressure as a way to stabilize the spacecraft, while improving the algorithms we apply to its data here on Earth to allow the mission to continue. Just last week, the TESS, Transiting Exoplanet Survey satellite, successfully launched to search an area of the sky 400x larger than what Kepler has focused on. The James Webb Space Telescope will allow us to explore periods of time we've never observed with a satellite with its capabilities before, and NASA's InSight Mars lander is expected to launch in May and study details of the Martian subsurface and geology with plans that could inform our understanding of how the rocky planets in the solar system initially formed. 61 years after an orbiting beach ball made history, we've no shortage of missions to fly and exploration to conduct.